Okay, I'm going to finish up with a full example of how you might do this in your IAs. And so let me just tell you what I did in the experiment in the IA. So I dropped, to determine the acceleration due to gravity, I dropped an object from rest. And if it's from rest, as you know, well, u becomes 0, so we have this. Now, you should be clear about this before you start anything. You should know what it is you're trying to do, data you're trying to collect, and what data you need to graph. Now, I'm trying to find A, of course. Now, this is already in the form of a straight line graph. So you can see that if I put S, the displacement, on the y-axis, and if I put t squared on the x-axis, then the gradient will be half of the acceleration, and that's what I'm trying to find. So the acceleration will be 2 times my gradient. So that's the goal here. So I need to measure some s values and some t values and go ahead from there. So just to summarize, I'm not going to draw the whole table, but I have my distance in meters, and my uncertainty in my case is 1/100 of a meter, 1 centimeter. And over here I have my time, which is in seconds, and plus minus 100th of a second. Now I chose those values, I determined them in the report. You can go and look to see how I justify that and what instruments I used. And I did trial 1, trial 2, trial 3. Now I don't want to write out all of these pieces of data, but I have lots of data. Just putting the x's here because I can't be bothered to write out the numbers. First step then was to average those time values. So I came up with a new table. So again, my displacement. And I had a set of values. They're just unchanged, rewritten from the previous table. Now here was my average time. And again, with an uncertainty of 100th of a second. The uncertainty doesn't change in this case because I took 3 values, added them together and divided by 3. You do the same with the uncertainty, and the uncertainty doesn't change. Now remember, I don't want t, I want t squared. So this is where I start processing the data properly. Again, just rewriting displacement from the previous table. Now I have the average time all squared. Okay, let's see. Okay, now this is where it gets a little tricky, because when you're obtaining t squared, remember that you're taking t and multiplying it by itself. So to get the uncertainty in time squared, I need to process that with the fractional uncertainty. So this is where it gets a little bit complicated. So I'm going to leave the uncertainty in a blank column over here. The reason is that because you're dealing with fractional uncertainties, which is taking the absolute uncertainty divided by the value itself, because the value itself is changing all the time for time, then you're going to end up with different uncertainties for each time point. Okay, each data point rather, I should say. Okay, so I'll just do a little example here. The first data point up here in the table above, so we have up here 0.5 meters, and I have 0.33 seconds. So of course this one just goes straight down there. Now average time all squared gives me 0.11 seconds. That's just 0.3 times itself. But what do I put for the uncertainty here? Well, remember, the fractional uncertainty in the time squared, well, I have to add the fractional uncertainties for the time. So I have delta t over t, square it, so I add it to itself, delta t over t. Now delta t, the uncertainty in the time, as you saw in the previous table, is 0.01 seconds divided by 0.33. Do the same again. then this gives me a final value of, please wait, 0.06, and that repeats, okay? Now, this is the fractional uncertainty in my t-squared value. So the absolute uncertainty in t-squared is that, and now I can get the absolute uncertainty, sorry, this is the fractional, the absolute uncertainty just by rearranging this equation. And rounding it up, I get 0.01 seconds squared. So here we have 0.01. Now, as it so happens, in all of my values, rounded up to the smallest that I can make it, it turned out that this was the same all the way down. Now, of course, the fractional uncertainty was actually changed, the absolute uncertainty in this column here was changing, but rounding them gave me 0.01 for all of them, okay? So now I'm in a position to make my graph. So my graph, we have S, the displacement on the y-axis, t-squared on the x-axis. Now, we draw in the absolute uncertainties on the data points. Now, as it turns out, on my graph, when I made it, the vertical error bars were so small you could hardly see them. The vertical error bars and the horizontal error bars are you depicting the absolute uncertainty on the graph. And my horizontal error bars were by far a lot bigger than the vertical ones. This is quite normal, by the way. You often have one uncertainty dominating the graph, okay? And when you continue this whole thing up, you ended up with your highest data point there with data points in between and something like that. And then I just simply told the computer to make a gradient the best fit through all those, and I was able to obtain my gradient, which came out as 4.9072 from the computer. The computer told me that, and as we saw earlier, I need to multiply that by 2 to get what I'm really after, which the calculator gives me 9.8144. Now, we are not done. In the next video, I'm going to show you how to get the uncertainty in this value, because we've been working hard to carry these uncertainties all the way through the procedure, and we go so far as to calculate them here and put them on the graph. But if you don't do anything with them, then it's a waste of time, okay? The whole point of the error bars is to say that you're not completely confident in this value. There's some uncertainty as to how close you are to it actually, and that's, I'll explain in the next video.